Good morning, students. In today's lecture, we'll talk about the next theory which explains bonding in coordination compounds. And the theory is crystal field theory or CFT. Now, theory first was valence bond theory, and it is having certain limitations, some drawbacks. That's why requirement of other theory was there, that is CFT. Now, what are the limitations of valence bond theory first? Valence bond theory does not tell anything about strong ligands and weak ligands. We have seen that in presence of NS3 as a ligand, pairing of electrons takes place in central metal atom or central metal ion. But while on the other side, in presence of F- as a ligand, pairing of electron does not take place in central metal atom or central metal ion. Pairing of electrons in central metal atom or central metal ions. Why pairing is there in presence of NS3 while pairing is not there in presence of F-? It was not cleared by valence bond theory. It means valence bond theory was not having idea about strong ligands and weak ligands. Limitation number second. It does not make exact prediction about the complex in which 4 ligands are there. Whether the geometry will be tetrahedral or geometry will be square planar. So there is no exact prediction about the geometries of the coordination compound where 4 ligands are there. It does not tell anything about the color of the coordination compounds. And last, it involves lots and lots of assumptions. That's why the need of new theory was there, and that was crystal field theory. So what are the important points related with the crystal field theory? Valence bond theory gives covalent treatment to the bonding present between central metal atom or central metal ion and the ligands. While crystal field theory gives ionic treatment to the bonding present between central metal atom or central metal ion and the ligand. So the bonding between ligand and metal, central metal, is ionic in nature. Second point, it treats ligands as the point charges. If negative ions are there, it is minus. Or if neutral molecules are there, then these are dipoles. Then the next point about crystal field theory. The degeneracy of d orbitals is broken down in presence of ligands when ligands are approaching central metal atom or central metal ion for bonding. It means when ligands are approaching towards central metal atom or central metal ion, then the d orbitals are broken down into 2 different set of orbitals. First one with the more energy, second one with the less energy. So before we start splitting in d orbitals in coordination compound according to CFT, let us have a look over d orbitals. D orbitals are classified into two types. First one is axial d orbitals and second one is non-axial d orbitals. Axial d orbitals, in which the lobes are located along the axis, are present on the axis. These are called axial d orbitals. We are having two, dx square y square and dz square. Dx square y square, two lobes are there. First on x, other one is y. Dz square, there is one is a nodal plane and there is one lobe over the z axis, dz square. Then we are having non-axial d orbitals when lobes are present in between the two axes. So first one is dxy, the lobes are there between x and y axis. Then we have dyz, the lobes are there between y and z axis, and then we have dxz, the lobes are there between zx and z axis. About octahedral complex or octahedral geometry. Remember, whenever we talk about octahedral geometry, then there are 6 surrounding species. And here the surrounding species will be ligands. And all the 6 ligands are present on the axis. Total 6 ligands are there. 2 ligands on x-axis, 2 ligands on y-axis and 2 ligands on z-axis are present if we talk about octahedral complex or octahedral geometry. It means all the axes, all the ligands are located on the axis. So what happens? Let us see. Let us see crystal field splitting in octahedral complex. So here is the energy profile diagram for the d orbitals of central metal atom or central metal ion when it is involved in formation of octahedral complex. So here I have drawn d orbitals in free metal ion or free metal atom with the lowest energy, or it is the energy in the ground state. Now what happens? When ligands are approaching towards the central metal atom or central metal ion, according to crystal field theory, the ligands are treated as point charges. And whenever a charge is there, then it is always associated with the electric field. So ligand which is approaching towards the central metal atom or central metal ion is approaching with the electric field. This electric field is having repulsive interaction with the d orbitals of the central metal atom or central metal ion. According to rule, whenever repulsive interactions are there, whenever repulsive forces are there, then energy of the system always increases. So what happens here? Due to repulsive interaction, energy of d orbitals increases or d orbitals are uplifted. So here I have drawn 5 d orbitals with increased energy. This is uplifted d orbitals in presence of ligands if the field is symmetrical. If this ligand is having equal repulsive interaction in all directions, it means the electric field is symmetrical or spherical in nature. In that case, energy of d orbitals will increase up to same amount. Remember, all the 5 d orbitals, means 2 axial and 3 non-axial, are degenerate in nature. They have same amount of energy. So orbitals with same energy are called degenerate d orbitals. So what I have done? I have uplifted the energies of the d orbitals in presence of ligand if its electric field is spherical or symmetrical, but this condition is hypothetical in nature. Ligands does not exert symmetrical electric field in all the directions. they will exert more repulsive interaction in the direction from where they are approaching towards the ligand. So let us see the arrangement of ligands around the central metal atom or central metal ion in octahedral complex. So here at the center we are having Mn plus, that is central metal atom or central metal ion. Now here we are having two ligands approaching from the x-axis, two ligands approaching from the y-axis, and two ligands approaching from the z-axis. So ligands are approaching from x-axis, y-axis and z-axis. So the d orbitals which are located on this axis will feel more force of repulsion, and the d orbitals which are not there on the axis will be having less repulsive interaction. So if you check that we are having two axial orbitals, first one is dx square y square and dz square. So here we can say that for dx square y square the load will be located on x and y axis, and for dz square the load will be located on z axis. It means there are two d orbitals which are located on the axis, and the two orbitals are dx square y square and dz square. So definitely ligands will have more repulsive interaction on the axial d orbitals in comparison to non-axial d orbitals. So what will happen? What will happen? Energy of axial d orbitals will increase and energy of non-axial d orbital will decrease. It means they will be splitting in the energies of d orbitals in presence of ligands. So we will get first set of d orbitals with low energy. We will be having second set of d orbitals with more energy. It will be non-axial, which are treated as T2G according to symmetry. It is not our concern. And there are two d orbitals which are treated as EG according to symmetry. It is not our concern. So dx square, y square and z square is having more energy than dxy, dyz and dxz. So degeneracy of d orbitals have broken down. We have obtained two different set of d orbitals, one with lower energy, other with higher energy. Now this energy difference is represented by delta, which is called CFSE, crystal field stabilization energy, or it is also called crystal field splitting energy. Because we are talking about octahedral complex, that's why it is represented as delta O. Crystal field stabilization energy or crystal field splitting energy for octahedral complex. In this manner, degeneracy in d orbitals have broken down. Now what will happen? What will happen? We will obtain d orbitals having energy difference. This energy gap or energy difference is called delta O. Now, there are some ligands which are having a strong electric field. If electric field will be strong, then repulsive interaction will also be strong, as a result of which the splitting pattern will increase. The value of delta O or the magnitude of delta O will increase. There are few ligands which are having weaker electric field, will be having weaker repulsive interaction. So here the splitting will be less, the value of delta O will decrease. So ligands which causes more splitting, which is having more magnitude for delta O, are called strong ligands, and the ligands which are having less value of delta O are called weak ligands. Based on the magnitude of delta O, these ligands can be arranged in the order of increasing value of delta O. As a result, we will obtain series of ligands, arrangement of ligands, and this arrangement or this series is called spectrochemical series, where ligands are arranged in the increasing order of their crystal field splitting energy. Now, what happens in presence of tetrahedral complex? It is the case of octahedral complex where ligands are approaching from the axis, and the d orbitals which are located on the axis gets more repulsive interaction and the energy increases. Now, in tetrahedral complex, none of the bond or none of the ligand will approach from the axis. It is always in between the axis. In tetrahedral complex, there is no bond which is located on the axis. All the bonds are non-axial. So definitely the d orbitals which are present in between the axis will feel more repulsive interaction, as a result of which, in case of tetrahedral complex, the energy of T2G will increase and energy of EG will decrease, because the ligands are approaching not from the axis but from in between the axis. So in tetrahedral complex, this splitting pattern will be just reverse. Here we will be having T2G, that is dxy, dyz and dxz, and here we will be having Eg, that is dx square, y square and dz square. It will be reversed, and delta O will be delta T, crystal field stabilization energy in tetrahedral complex, or crystal field splitting energy in presence of in tetrahedral complex. Remember, the magnitude of delta O is always less than delta T. Reason is very simple. In octahedral complex, there are 6 ligands which are approaching towards the metal atom or metal ion, while in tetrahedral we are having only 4 ligands. So repulsive interaction due to 6 ligands is more than the 4 ligands. So always the magnitude of delta O is more than delta T. It is found that delta O is nearly 2 times of delta T. So it is all about crystal field stabilization energy or crystal field splitting in octahedral complex and tetrahedral complex. Now, about filling up of electrons in d orbitals in T2G and Eg. So here one point is important. Point is, we have to see whether we are provided strong ligands or weak ligands. If strong ligands are there, then this splitting energy is more. And if weak ligand is there, then this splitting energy is less. This difference is less. So what will happen? Just see. If you are provided strong ligands, then pairing energy, that is P, is less than delta O. So how it will affect the distribution? Suppose we want to accommodate 3 electrons. So all the 3 electrons will be accommodated here, 1, 2 and 3. Now about the 4th electron. Suppose we want to accommodate 4 electrons. So where we will place 4 electron? In T2G or in Eg? Because strong ligand is there, so splitting energy is more than the pairing energy. If we want to send electron to higher energy, it will require energy. If you want to send electron to Eg, it will require energy. And if we want to pair electron, then it will also require energy. Here, pairing energy is less than the difference, that is delta O. So electron will be filled here if ligands are strong. If ligands are weak, then this splitting difference will be less. In that case, pairing energy will be more than delta O. It means if we want to pair an electron in T2G, we will require more energy in comparison to sending the electron to EG orbital. So if we are having 4 electrons to be accommodated in T2G and EG in presence of weak ligand, then what will be the arrangement? 1, 2 and 3. And electron number 4 will move to EG because the difference of energy is less. In this manner, electrons will be accommodated in d orbitals in octahedral complex if strong ligands or weak ligands are there. We have to fill electrons in T2G and EG. Now, CFT also explains color of the compound. How it explains? It tells that if unpaired electron is there, suppose one electron is there in T2G, in central metal atom or central metal ion, then this electron will absorb energy from the visible region. As a result of absorption of energy, the electron will be transferred to higher energy states EG, where it is not stable. So when it will come back to T2G ground state, then it will emit radiation which lies in visible region. So if unpaired electron is there and it is absorbing energy from the visible region, then definitely the complex or the coordination compound will exhibit color. In this manner, color can be explained by the help of crystal field theory. That's all in this chapter, and that's all for today. Thank you and have a good day.